or the bacteria. When something's growing weak in a weak manner, nature says you're not fit, and she comes in and cleans things up. That's how I see it. I think there's a bunch of science that could back it up if you'd like, but we don't need to go there if you don't want to. Anyway, A&L, which some people know about, which I think is around here somewhere, used to be called A&L. It's not called A&L anymore. Waypoint is one of a few good Albrecht-style labs in the country. I have a report here from a place called Logan Lab, which is in Ohio. I like them because I can get things like cobalt and molybdenum and selenium and silicon, along with about other 14 elements for $30, which is the best price I've been able to get for so many nutrients. So we have Logan's form available on our website organizationally. Not saying you should use Logan. I'm saying any Albrecht-style lab will work. There's Midwest Lab as well, which is another good Albrecht-style lab. But basically, the way you take the test determines the numbers you get on the report. And so you can't take two different kinds of tests and read them the same way because the numbers mean different things. For those who want to go into the details, let me just give you one example. I'll use the example of phosphorus. Phosphorus is an element that is tested in various different manners. There's the Bray 1, there's the Bray 2, there's the Bray 3, there's the Malic, there's all kinds of different acids you use to test phosphorus. UMass, where I went to school, uses what's called the Malic 3 analysis on phosphorus, and Logan Labs uses the Malic 3 analysis on phosphorus. And and what we did was we split a soil test and sent half of it to UMass and half of it to Logan. And when we got the reports back, Logan said 150 parts per million phosphorus, and UMass said 6. Yep. So not sort of close. 150 and 6, right? That's like a lot. 2,000%? Ballpark? 2,500%? 2,500%. I think. Whatever. It's a big difference.
Any ideas why that would be?
And that's my point. My point is, we like... What? So we called them up. And in conventional ag, in the philosophy of conventional ag, we understand that phosphorus is an anion that ties up readily, and it's difficult to make it soluble. And so UMass figures that 95% of your phosphorus is not available because in conventional systems it's not, and so they just delete it off of your report. There's an algorithm in there which says delete 95% of the phosphorus. Because you don't have life in the soil, and life is the one that actually makes phosphorus available. So people may have heard of mycorrhizal fungi, which is, really cool stuff. Mycorrhizal fungi, cool people. They're really good at solubilizing phosphorus. If you've got a well-functioning biological ecosystem, you don't need to have much phosphorus in the soil because the mycorrhizal fungi will pull what's there and feed it to your plant. Phosphorus gets cycled through and through and through. It doesn't get harvested out really. What's that?
There's a lot of non-mycorrhizal.
There are non-mycorrhizal plants, and there are other, species of bacteria and fungi that also solubilize phosphorus. But just simplifying it down to a very rudimentary level, the concept here is that in a conventional system where you apply fungicide and you use tillage, you don't have life in the soil, and therefore these nutrients aren't available, and therefore you need to add fertilizer. Anybody heard of phosphorus leaching and the plumes? Was it Lake Erie that they had to shut the water down in Toledo for a while, or I can't remember who it was. This massive plume, right? In Vermont, you can't apply fertilizer anymore because Lake Champlain has got all these plumes because it's not phosphorus per se, it's the soluble phosphorus that comes in triple superphosphate that you have to add because your fertilizer, because they don't make any money if you don't sell. If you don't buy fertilizer, the fertilizer company doesn't make any money. The fertilizer company is the one that's giving money to the university to make recommendations. You guys know how this works. Everybody know how this works? You know how this works. Okay, so that's the basic broad strokes rationale why I'm going to be recommending not a Land-Grant University soil test, but a Albrecht-style soil test, which means if you've got a Land-Grant University style soil test, it's probably, I can't help you with that. Don't take what I'm about to teach you and apply it to your land-grant university soil test. Don't do it. It doesn't work. It's a different, their numbers mean different things. Even though it says boron, even though it says phosphorus, it's coming from a different perspective, and so it's really a different language. That all being said, I'll just sort of run through a few points here that I'd like to talk about. I'm sorry, this has been photocopied a few times, and so it's hard to read, but most of the numbers there, well, we'll deal with them when we get down to them. Exchange capacity is something I want to talk about for a second, then we'll talk about pH. Well, first, sample depth at inches. For those who have never taken a soil test, the process of taking a soil test is one where basically they recommend you go down, you take a core that's 6 inches deep. It's assumed that the 6 inches is the aerobic zone where there's air in the soil, and below that there's no air, so there's no life, and so it doesn't really matter too much what's going on down there. Ideally, you have a deeper aerobic zone, but the general assumption is, if there have to be assumptions, because we're going to be doing math with numbers, you need to make set some basic guidelines. The assumption is you're taking a 6-inch deep core. I would suggest you take multiple cores from your field, at least 5 or 6. People ask how big is a field, and it depends on the lay of the land. If the lay of the land is similar across the entire area, you could have a 20-acre field. If it's different, you got high and dry here and low and wet there, you could have, you need 2 soil tests for your backyard, right? It has more to do with the lay of the land, how big your field is, than any, formal set volume. So look at what plants are naturally growing there. If you got similar plants growing in an area, that is probably going to give you a similar, you're probably going to have a similar soil type and mineral levels. You want to take multiple cores, mix them up in a bucket, take a pound out, stick it in your Ziploc bag or whatever, fill the form out and ship it in. Critical piece is you want to make sure that you're checking, if you're doing the Logan test, you want to be checking the box that says Base Plus or Agridine 2. If you download the form off of our website, which gives you the deal price, it's called the consultant price. You know how this works?
Yeah. I have that.
There's like a
also
little
with
kickback.
If anybody wanted to use A&L, I think Logan may do more.
This is a
More
special
like
deal. This is a Jerry Bernetti set this up, this test. But generally, they've got the price for the general consumers, and then they've got the price for consultants. And the consultants pay half as much because they give business, right? You know how this works?
Yes.
Right. So what we have is we've got the consultant test form on our website, so you don't have to pay as much. If you go to their website, you're not going to find this. Just saying. So you can do whatever you want. All right.
What about sample?
What's that?
I was confused. That, going to their site rather than your link.
If you don't go to the link, you're not going to find it because this is not, yes, money.
He's taking conglomerating buying power, so like, it's what I do with
I
A&L. Like,
understand.
if you send
Yeah,
this
he-
sample,
he's
you
got
go,
it-
"I
he's got it
calculated
now."
On A&L,
Yeah,
you're gonna get a consultant rate, and I just pass that on, so it's a discount.
right.
It's only a 10% that I get A&L, because I don't do a ton of samples.
Yeah.
I just did the Google search instead of
Follow the link on the registration form.
I got the wrong information.
It probably said on the email what to do,
Oh, it did.
and then you didn't listen. Yeah, exactly. Yeah. Why should I trust these characters? They're from up north, anyways. Yeah. All right.
What about on depth of soil testing? I always think it's better to get some more depth so you know what minerals you got down below that the plants can bring up over time.
So it depends entirely on what you're growing. If you've got a perennial polyculture, you probably should be looking down deep. And the question also is, what's your soil compaction? If you've got a plow pan at 6 inches, it doesn't matter what's at 7 inches because your roots can't reach it. You should have a 2-3 foot deep aerobic zone, but most people don't. So what matters is what's there. And then we can talk about the whole conversation about whether you need to add minerals in the first place or whether they're in the subsoil and your plants can bring them up. And if you're growing annuals that have 6-inch deep root zones all the time, nothing's coming up. But if you've got a nice, polyculture with trees and grasses and everything else, then you can have things being cycled up. And then you really should do like a 3-foot soil profile to see what's in your underlying geological material. And you still may not have certain elements, but there's I am simplifying a really sophisticated conversation down to absolutely rudimentary right now. So understand that. This is not, I'm not able to go as deep as I'd like to because I haven't put aside enough time for the conversation.
So if you tilled it, say once or twice this year.
Yeah.
You've already turned the ground.
Yeah,
So, 6 inches is still, it's 6 inches, you've already tilled it up. You know what I'm saying?
so it's pretty much universal already, so you don't need to bother with the core,
Right.
Yeah.
Okay.
plus or minus. Use common sense. Common sense, right? People can tell you something, or you think you heard somebody say something to you, but then your common sense tells you, I don't know. Who do you listen to? People that gone to school, they listen to what they think the teacher told them.
Yep.
People that are farmers, no, they shouldn't really trust anybody if their common sense disagrees with what that person says. Right? As far as I'm concerned, we've got intuition. We're hardwired with the capacity to perceive reality directly through frequency, just like nature does. We'll talk about this later. But that's basically our gut feeling. That's basically what knowing it in your heart means. Because we got antenna systems we're hardwired with. Right? We got antenna in our gut. We got antenna in our heart. And we know about this?
Yes.
Yes. It's totally cool. It's really, really cool. Anyway, so, yes. If common sense disagrees with what you've been told, I would say disagree. Yeah, don't do what you think you've been told. All right. Exchange capacity. I'm not going to have time to finish this whole topic before lunch, but that's okay. Exchange capacity, people may have heard of this concept of exchange capacity. We generally say cation exchange capacity. There is anion exchange capacity. What Logan measures is what's called total exchange capacity, which is the cations and the anions. Anybody who's taken a basic agronomy course or master gardener's course has heard about this whole sand, silt, and clay thing. We know about sand, silt, and clay. So we got our sand here, we got our clay here. We'll just do the sand and clay. The idea here is basically that we have similar volumes of space here and here, but we got way more surface area here than here. And it's not the sand or the clay that the plant is eating, it's the elements that are attached to the sand or clay. Right?
Well, when they're soluble in
However the plant gets access to them, it's the elements that are attached to the sand and the clay that the plant is eating, not so much the sand or the clay. And we know what sand and clay are made out of? What are the elements?
Silicon dioxide. And
Silicon, oxygen,
And aluminum.
Aluminum
Silicate.
and iron. Silicon, oxygen, aluminum, and iron is the vast majority of soil. Silicon, iron, aluminum, and yeah, that's it. So anyway, so we have these elements that are attached to the soil. We got our calcium, we got our magnesium, we got our copper, we got our zinc, etc. So exchange capacity basically is telling you how many of these nutrients are in every unit of space in the soil. So the more surface area you've got, the more capacity you have for the nutrients to be there. That make sense? If you have not much surface area, you have not much ability for your soil to hold much. So I like to use the metaphor of a gas tank. Anybody ever rode in a motorcycle? How much gas does a motorcycle gas tank take?
Yeah.
You can buy 10 gallons of gas, and you put that into the motorcycle gas tank, and it'll just end up on the road, right? It can only hold so much. So a sandy soil can only hold so much. The tank is only so big. You can put down all you want, but it doesn't really matter. It can only hold so much. And when the tank's empty, it doesn't need much to fill it. But when you got a clay soil that's empty, it takes a lot more to fill it. So if you ever driven an F-350 or any kind of a decent-sized pickup truck, right, 30 gallons later, you got a full tank. But you can do a lot more work with that full tank of a F-350 than you can with a motorcycle. So a high exchange capacity soil, a clayey soil, can hold more nutrients. It has a greater yield potential, but when the tank is empty, it takes a lot to fill it up. That's what exchange capacity is in short. I mean, I've got a few basic points here to convey the concept. Is that a question?
You don't have to do it now, but at some point, could you talk about the relationship between biochar and exchange capacity?
I'll put biochar on the list. That's a good topic to have. Yeah.
What's the sort of typical exchange capacity of a real sandy soil?
4, 5, 6. They generally say 8 to 12 is normal, whatever that means. You go out to California, they're all 20, 25, like, oh, really? You go to New England, you got 6s and 7s and 8s. That's why all the farmers left New England.
Why in California so hot?
Because they don't have so much rain, and if you weather the soil over thousands of years, you actually you wear off these bonding sites, and so you've got weathered clays and you've got high energy clays, and so basically because it doesn't rain so much, their soils aren't so weathered, and they've got a larger inherent holding capacity. What has way more holding capacity than clay is organic matter. Right? Organic matter is this fractal structure that's got bonding sites all over the place. And so it doesn't really matter, I don't think, that much what your exchange capacity is. It is what it is. You got your land, you're not going to move. I guess some people do, but generally you got the land you're working with. You can increase the exchange capacity by building organic matter, which you do by growing healthy plants. Anyway, I don't want to spend a lot of time on this. Just touch on the topic for those who haven't heard of it before. What I do want to talk about is pH, because I think a lot of people consider pH to be important, and I thoroughly don't. And I want to explain why and what pH actually is. So let's just start with a question of what is pH?
Power of the hydrogen ion.
Power of hydrogen. Almost. No. Something about hydrogen.
Measures acidity and bases.
What is acid and base? What is pH? Testing. How much hydrogen there is.
Hydrogen ions and hydroxyl ions.
There we go. It's the inverse log of the hydronium to the hydroxyl ion. Really?
Yes.
I'm going to explain to you. It's real simple. It's real simple. If they understood it, if the teachers understood it, they could explain it to you so you'd understand it. But they don't understand it, so they don't explain it to you so you can understand it, right?
Right.
Right.
You know how this works?
Yes.
No, we don't know how it works. Explain it.
Exactly. No, I don't. You keep telling me it's important, but I don't understand. All right. So we've got this molecule. People have heard of this one.
Yep.
Yep.
HOH, H2O, water. So the concept here is that you've got the water molecule, but you don't really ever usually find a molecule of water, right? You find water together, with multiple molecules together. And the thing about water, one of the things about water, which I do think I understand, is that they say water is bipolar. It's got a positive and a negative pole. And so you have the H's and the OH's are kind of hanging out together, but they're kind of screwing around. Right? And so this H sometimes is hanging out with this OH, and sometimes this H is hanging out with this OH. There's a positive charge and a negative charge, and they're vibrating, and they're never ever really just over here. They're not monogamous, right? They're not. Apparently they're not. So what happens is, depending on the environment, you never have an exact balance of H's and OH's. You have always a few more H's or a few more OH's. It's like musical chairs. There's never quite enough for everybody. And so what pH is, as I understand it, is how many H's you've got to how many OH's. So pH of 7 means you've got 1 H for every 1 OH. That's a perfect balance. Everybody's got a seat in musical chairs. pH of 6 is 10 H's for every 1 OH.
Yeah, for the power 10.
It's a log. It's a log. The inverse logarithm. That's a math thing. pH of 5 is 100 H's for every 1 OH. pH of 8 is 1 H for every 10 OHs. People see basically how it works?
So my soil is Lenore, and according to the soil survey, it wants to be 3.4.
Wants to be 3.4. It is 3.4.
In nature, it is, under the trees, it is 3.4.
And that's what we call a thoroughly worn out soil.
That's what I try to grow in.
That's not.
And that's why all the boys that grew up in Appalachia had flat feet and bad teeth, is because their soils that were growing the food they were eating, which was building their bodies, didn't have in it what their bodies needed to function well. How does this work? What is it? So a pH of 3.4 means you've got a hell of a lot of H's. So instead of having zincs and coppers and magnesiums and calciums, you've got H and H and H and H and H and H. You've got a soil that doesn't have any minerals in it. It's got a bunch of hydrogen. Yeah? What happens when the soil life is fed by the plant? I didn't tell them about this, but the plant will make specific food for copper solubilizers if it wants copper, or make specific food for phosphorus solubilizers if it wants phosphorus. So the plant says, I want copper, and it adds amino acids to the sugar to make it food for the copper solubilizers. It injects it down into the soil where it knows what the copper solubilizers are. They go down there, and what they do is they exude acids or bases to solubilize the copper off of the soil, and they eat it. And there's still this charge hanging out here, and so they replace the copper with the hydrogen. And when you do that over and 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 over again, you pull all the minerals out, and you're stuck with a lot of hydrogen, which means you've got a low pH. And the university says, you got low pH, add limestone. Why do they think you want a higher pH? Why does the university tell you to have a higher pH?
That's what the plants want.
Why?
Because
So that
they're
the
so
amino
wide.
acids work better to.
No, the university does not acknowledge that this happens at all.
Oh, okay.
University, we already went off the reservation with this. This is officially not part of, if you study agronomy 101, maybe you're starting to learn this, but Elaine Ingham was one of the first people who even said this is possible. And that was only a couple decades ago. And people may have heard of Elaine Ingham, but what she's talking about still hasn't made it into the university agronomy protocol, as I understand it.
They relate pH to acid and basic.
Why is it considered to be important? Why
They
is,
give you a chart of nutrients that say they're only available in
Thank you.
pH ranges.
Yes.
Say that again.
They give
I'm
you
gonna
a
draw it
chart
up here
of all
then.
the minerals that plants need, and then they show you the pH scale, and they hone down on the range where most of the minerals are mostly available. Because some of the minerals aren't available at low, but they're not taking into account that the plant has all these microclimates, and the biology creates all these microclimates, and
so,
anyway.
I'm going to draw it up for you. It's the test tube. Got it? Stick figure. I'm really good at stick figures. I got a couple of them. I'm going to put a piece of copper in here. Piece of copper in a test tube full of water. So, in chemistry, in a chemistry set, depending on the pH of the water, the copper is more or less soluble. True. Fact. So what she was talking about is there's charts in the agronomy books, if you look at them, and they'll have this, solubility gradient, and they'll say copper is most soluble in this 6.4 to 6.8 range. In a test tube, totally true. A couple things missing here in the test tube. There's no soil, there's no life.
Yeah.
Right? Conventional ag is based on chemistry set experiments. they don't take into consideration that what these soil life do is they raise and lower pH